Welcome back, students. Let us now begin 3.2 linear correlation. In the previous section, 3.1, we went through several different types of bivariate data sets. Depending upon their nature, we had to do something different. For example, if we had two qualitative variables, then there isn't much we can do because we cannot do any kind of measurement except for counting. So all we could do was to produce and analyze contingency table. If we had at least one quantitative variable, then we could produce histogram, ORGIV, box whisker chart, whatever, and then compare those side by side. Now, if we have two quantitative variables, then it was possible to produce scatter diagrams kind of like these. For example, x-axis represents the midterm exam score and y-axis represents the final exam score. Both are measurable, so we could represent each student's performance as a point on xy plane and then put those into scatter diagram kind of like these. Now, figure 3.9 roughly classifies the types of different scatter diagrams. The first picture shows no apparent correlation. The second and third pictures show positive correlation, where the bigger the x value, the bigger the y value as well, or at least the more likely it is to be bigger. The final two pictures show the negative correlation. The bigger the x value, the smaller the y value. Now, there's another perspectives that I want you to remember, especially for the picture number 3, this one where my mouse is, and number 5, this one. It is relatively easy to visualize the line of best fit. And if the line of best fit is increasing, in other words, if it has positive slope, then we have positive correlation. And if it is negative, if the slope is negative, it is decreasing, then we have to have negative correlation. We can see those kind of things clearly from the picture number 3 and number 5. It's going to be a little bit harder for number 2 and number 4, but nonetheless they are possible. Please remember this line of best fit idea for the next section, 3.3. That's going to play a huge role in the next section. But for now, let us concentrate upon some single quantity called correlation coefficient, which is defined like this. Now, let's continue our discussion in a little bit more detail in my notebook here, where I have a little bit more control. Let me increase the font a little bit further so that I can explain this thing better. This is how the correlation coefficient was defined. Xi, for example, is the midterm exam score of a certain student. Yi is going to be the final exam score. What is xi minus x bar? It's a deviation because x bar is the class average of the midterm exam. In other words, how much ahead that student was. Same for the final exam. This is the deviation. Now multiply those two deviations and sum them all up. That's how we get the numerator. In other words, if we have something like 20 students here, then this is going to be relatively tough computation with handheld calculator. You have to calculate all those deviations, all those subtractions, and then multiply all those together, and then add them all up. It's going to be rather heavy duty computation. Now, how about the denominator? N minus 1 is just dividing by a single number, okay. But what are these? These are standard deviations. And here's a reminder. What is the standard deviation? Sample standard deviation, to be a little bit more precise. This is the way we define a sample standard deviation. Deviation squared, sum them all up and divide by n minus 1, the degree of freedom. That forms a standard deviation of x, and we have to do the same thing for standard deviation of y. In other words, the denominator computation is also very, very complicated computation. So if I have about 20, if I have a sample size of about 20, this is going to take a long time for you. So I don't think I'm going to ever write any exam problem or anything like that, even homework problem, for those kind of stupid brute force computation. Instead, let's work those out using some technology aid. One way to handle it is to use Mathematica, this very notebook, but there's a bit of a problem. The Mathematica is very, very powerful, but it's expensive and it's not easy to learn. So let's make a little bit of compromise. Let's focus upon MS Excel. Here in 2.3, I have a summary of step-by-step process how to calculate those. But I'd like to save some time, so let me open up an Excel file and let's work it out. By the way, the example that I'd like to work out is this example, example 2.5. If you have a class score distribution, kind of like this, exam 1 and exam 2, so you can find a correlation between these two. And homework 1 and homework 2, yeah, you can do something similar, and many other things too. That's something I'm going to do. Okay, I just opened up an Excel file, the same file, as a matter of fact. Actually, no, it's not the same file, excuse me. This is Excel file, not Mathematica file. The same data set, that's what I meant. And we have exam 1 scores here, the midterm exam, and exam 2 scores there. And let's practice how to calculate the correlation between these two. Let's say X is exam 1, or let's put it like this. And exam 2 is Y. Okay. First, how do you calculate the average? We have done this before in chapter 2, so let's review this as quickly as possible. Just highlight all this and then go to, actually no, excuse me, I have to go here first, because if I highlight and calculate average right away, and the printout will go to its default position down here, as a matter of fact. And I want it here, so we have to start from this box and then go to this sigma where we do all kind of computation, and then sum. The next one is average, so let's take the average, and we don't want the default, we want this data set. Select it, click enter, and then we have the average. Let's do it again. Use this box and then go to the same thing and then take the average of, not the default, this data set. Click enter and then we have the average. Okay, good. Now let's continue just a little bit more of review. Let's do standard deviation. We have done this in chapter 2, but let's review it again. Let's go to computation package here, sigma, and then we have to find our standard deviation, which is not here, so you have to go for more functions. Okay, the default is most recently used, and actually I have used standard deviation before, so it comes right over here, but let's pretend we don't see it. Let's suppose you're using a public computer and you don't see anything like those. In that case, you have to select the appropriate category and find statistical here. And then find standard deviation way back in S, and there are going to be two of them. Yeah, standard deviation .p, this is population standard deviation. That's not what we want. This one, standard deviation .s, standard deviation for sample. This is what we want. Click OK. And then in this array, in this box, we have to select appropriate data set. Using my mouse, I select it. OK. Click enter or just click OK. I have the standard deviation. OK. One more review. Look carefully. Let's do the same thing with Y. Go to computation package, more functions, and then find statistical. If it were in some other place, find statistical category and look for standard deviation. sample standard deviation to be a bit more precise. So we need .s, and then we have to select the data set we just did. Click OK, and we have the standard deviation. Now let's do correlation. Okay, pay attention here, this is new. We do the same thing. Statistical package, more functions, find statistical category if it were in some other place. Go to statistical, and then find correlation. It's in C. Correlation requires two data sets, two variables. So first data set, second data set. So array 1, here we need the first data set. So let's select exam 1, all these. That's selected. Don't click OK. If you do, you're going to get an error message. You'll have to start over. Go to now array number 2, and you have to select the second data set here. Use your mouse to select the second data set. Select it. Good. Either click enter or click OK. And there goes the correlation. Just one more exercise. Let's find out correlation for homework. Okay, we are doing these two. Okay, I'm going to present it here. Go to statistical package. It's already in statistical, all right. And find correlation. Click OK. Array number 1 will be homework 1. These are computer homework, for example. Okay, select it. Oops, I clicked something wrong here. Okay, got it back, all right. And then move your mouse and click this array 2 to begin array 2. And you have to select homework 2, written homework problems, for example. And click OK, and there goes the correlation. As you can see, correlation coefficient is bigger for homeworks than the exams. Okay, we just went through how to calculate correlation coefficients using MS Excel, and here is a summary in 2.3. We have about 2 or 3 minutes left, so let's talk about some properties of correlation. And the property of correlation, please remember this property. R has to be between -1 and +1. R equals to 0 means no correlation, kind of like this picture here, where my mouse is. If we have strong correlation, then R value is either close to +1 or close to -1. Equal to 1 means perfect positive correlation, and in practice, this kind of thing is rare unless you cheat. Kind of like measure the height of all the people in your group and then represent those figures in terms of inches and in terms of centimeters. That way you're going to get a perfect correlation because basically you're looking at just one variable but represented differently. But in reality, those kind of things are really rare, and R value will be usually between -1 and +1. Okay, so let's look at some realistic scatter diagram here. Example 2.4, which represent the water levels between these two lakes, Levin Lake and Lake Tawakoni. And then I went to North Texas Water District website and then got their monthly water level picture. Because these two lakes, Levin Lake and Lake Tawakoni, are so close nearby, let me show you the picture, by the way. Here you go. This is Lake Tawakoni, where my mouse is, and this one is Levin Lake, where my mouse just moved to. As you can see, those are pretty close nearby, so if it rains around one lake, it's very much likely it's going to be raining in the other lake as well. So we expect very strong correlation. As you can see, correlation is 0.9, it's pretty strong. And if you look at the location of all those dots, then it shows pretty strong correlation. This is a kind of realistic example you can expect in real life situation.